Hello everyone, this is Meghana. In this video, let's learn about non-deterministic finite automata from a subject of automata theory and compiler design. So let's get started. Basically, we know that finite automata consists of a sub-branches called deterministic finite automata and non-deterministic finite automata, where NFA, that is non-deterministic finite automata, are the computational models which are generally used in the field of computer science and mathematics in order to describe and analyze the behavior of the system with finite states and their transitions, where these are applied in the field of computer science, in where basic for the branches of natural language processing, and also for pattern recognition, lexical analysis, and also for compiler designs. What is NFA? These are a mathematical model which describes a computation or a process. It consists of 5 tuples, where the first state is a set of states that are included in that transition, and a set of input symbols, a transition function, and an initial state, and also a final state or an accepting state. The characteristics of NFA are non-determinism, epsilon transition, and acceptance. These, like the non-determinism, are like unlikely deterministic finite automata, which is a DFA, where NFA can have multiple possible transitions for a given input symbol from current states. This non-determinism allows for more flexibility in the computation. Whereas in epsilon transition, NFA can have an epsilon transition which allows them to move from one state to another without consuming any inputs of it, which is just like a null character. These transitions are useful for representing non-deterministic choices and empty transition. And the final one is acceptance. An NFA can accept or reject an input string based on whether it can reach an accepting state after processing the entire input. It doesn't have to consume all input symbols to reach an accepting state. Deterministic versus non-deterministic. In deterministic, it's a type of finite automata in which each input symbol, like there is an exactly one transition from one, each state. But whereas in NFA, there is a multiple transition from each states. So let's take one example here. If Q1 is a initial state, Q2 is a next state, where here there is a transition from Q1 to Q2 with an input value of 0. This is the starting state, where we're going to represent with a arrow mark. Generally, this is DFA, which is deterministic, from where there is exactly one transition from one state to another. Whereas for NFA, there is a multiple transition from one state to another. Here Q3 is another state where there is a transition with the different input values, or it can be of same. This is an example for non-deterministic finite. So let's have an example for the conversion from NFA to DFA. Here is an example where the given transition diagram is an NFA. One second. Yeah. The first step we need to write is that the given transition diagram. Here there is a transition from Q0 to Q1 with a value input value of 0 and 1, and also there is a transition which is into Q0 only, like a self loop of 0 input value. Later the Q1 is there is a transition in between Q1 and Q2 of the value 0, 1, and with a self input like a self loop of 1, and Q2 is a final state. It's a final state where all the values are accepting. Q0 is a initial state where this summation symbol specifies the input symbols we are using. The next step is that the transition table. Here we are writing the transition function where against a 0, 1 means like the input value we have taken. At starting, Q0 is an initial state. We have taken Q0 as an initial state, and from Q0, the value input symbol 0 is moving to Q0 and Q1, because for Q0 there is a self loop, and for Q1 the one input value 1 is going for Q1. That's how we write the transition table for the given states, transition states, but there is a newly obtained state here, that is Q0 and Q1. Like we need to find the transition in between these two, like in the whatever the new states we have got, no, we have to find the values, like what are the input values they are fetting. So let's consider the newly obtained state, that is Q0 and Q1. If we consider Q0 and Q1 here, yeah, so let's continue. Like how we have to take is like where there is a 0 value, like the input 0 is moving from one state to another, we have to write the those states into the column of 0th input value. Here, no, the Q0 is having the state of 0, input value 0, and also there is a transition from Q0 to Q1 with a value of 0. And for 1, we need to consider for both the values, like for Q0 also and for Q1 also. For Q0, 1 is moving to Q0 to Q1, and the input state from Q1 we have to consider the input value 1 is moving to Q2, from Q1 to Q2. These are the values. After writing all this transition table, the next step you need to write the sets, like where a 5 tuples included. The starting state will be a finite set of states we have been used, and these are the finite set of input symbols. It is a transition function where it is denoted by delta. Q0 is an initial state or a starting state. F is final or accepting state. Write those values whichever you obtained in this table. Generally, if we know from the given diagram, Q2 is a final state, but why they have marked asterisk here also means has the final state is present in this state also, the newly obtained state also. So that's why we need to mark asterisk symbol for the accepted states. Okay, for starting state it has to be a arrow mark. After writing this step, after writing the third step, The final step is transition diagram, creating based on the transition table whichever we got, with the new input states. We have to create a transition diagram for that, where just write all the newly obtained and every states here. According to this table, write the transition with an input values. Like from Q0, there is a transition of input value 0 to Q0 and Q1, and a transition of input value 1 is from Q0 to Q1. This state is totally different from this state because this is a newly obtained state. This one is the given state. So let's move on with the next slide. Yeah, the conversion process involves transforming a non-deterministic finite automata into a deterministic finite automata. The main goal of this conversion is to simplify the automation and make it easier in order to analyze and understand. The conversion process involves creating a new DFA with equivalent behavior to the original NFA. And even for further moves, we are going to use regular expressions, where these are the patterns used to match or manipulate the strings, and they are the powerful tool for searching and validating and also for manipulating the text. Relationship with a non-deterministic finite automata, where it can be converted, regular expressions can be converted to NFA to efficiently match the patterns in strings. NFA are used in order to implement a regular expression in engines. What are the applications of NFA? As we all know, these are wide range of applications in various fields. The first application is based on natural language processing, where NFA can be used for tasks such as tokenization, part of speech tagging, and synthetic phrasing in natural language processing application. And also it is used in a regular expression matching. These are commonly used for efficient pattern matching in text processing applications such as searching for specific patterns or extracting information from a text. Lexical analysis, in the place of lexical analysis, it is used in compilers and interpreter for lexical analysis, and which involves tokenizing the input source code into meaningful units. And for DNA sequence analysis, NFA can be applied to analyze DNA sequence, such as identifying specific patterns or modifies in genetic data. Closure properties of NFA are that is preserved under certain operations, and in context of NFA, closure properties are important for understanding the behavior and capabilities of non-deterministic finite automatas. In conclusion, that NFA are a powerful tool in the field of computer science and automata theory. NFA allows a greater flexibility and expressiveness in representing and analyzing complex systems. By allowing multiple possible transitions for a given input symbol, NFA can handle a wider range of data or language patterns. However, this increased expensive power comes at the cost of increased complexity in terms of both construction and simulation. Despite these challenges, NFA are the fundamental concept in automata theory and have many practical application in areas such as natural language processing, pattern recognition, and compiler designs. That's all about NFA. Thank you.